Chapter 6, Friction Loss Principles in Application. So let's dive into it. Our objectives: explain the friction loss principles, recite the 4 fundamental rules governing friction loss in hose and pipes, apply the 4 fundamental rules governing friction loss to fire department hydraulics, and determine the rate of increase of the friction loss as the velocity flow in a hose layout is increased. Explain the various parts of the friction loss formula. Determine the friction loss in single lines in hoses when the size, the length, and the flow in the hose are known. Determine the friction loss in layouts of multiple lines of the same size and length, but with different flows. Determine the friction loss in layouts of multiple lines of the same size and same flow, but of different lengths. Determine the friction loss in different size multiple lines of the same length and the same flow. Determine the friction loss in multiple lines when the lines are of different size, different lengths, and different flows. Determine the friction loss for wide lines of the same size, length, and flow. Determine the friction loss for wide lines of the same size but having different lengths and flows. For years, there has been a debate on how fire hydraulics in the classroom differ from real-life situations on the fire ground. The objectives of this chapter is to provide a basic understanding of the friction loss principles and their application to hydraulic problems with the formulas in use today. If there were no friction loss in the hose lines, the pump operator's task would be extremely easy. As it is, however, as the water moves through the lines, sufficient pressure must be provided to overcome friction loss, in addition to all other pressure requirements, such as elevation loss and gain. Friction is defined as the resistance to relative motion between two bodies in contact. Friction loss in hoses can be defined as the loss of energy in the form of pressure due to friction. Friction loss formulas have been used since the 20th century. During the latter part of that century, a change was made to the friction loss formula and the factors in it. Now, most fire departments have accepted a formula that is the standard for fire department hydraulics. The formula we will be used can be written as follows: PDP equals FL plus NP. Simply put, that is the requested pump discharge pressure equals the friction loss in the hoses and the appliances plus the required nozzle pressure. The friction loss in hoses is the difference between the pump pressure and the nozzle pressure. For the friction loss formulas, we will be using a friction loss coefficient, which will be different depending on the hose size. There are 4 rules governing friction loss in hoses. Rule number 1. All other conditions being equal, friction loss varies directly as the length of the line. In the same size hose, friction loss varies directly as the square of the velocity flow. 3. For the same flow, friction loss varies inversely as the 5th power of the diameter of the hose. And Rule 4. For a given velocity of flow, the friction loss is independent of the pressure. To understand these rules, we need to understand these terms. Varies directly means that when one item increases, the item used for comparison also increases. Varies inversely means that when one item increases, the item used for comparison decreases. Rule 1 states that as long as the size of the hose remains the same and the flow remains the same, the friction loss for each given length of hose will also stay the same. So, if we have 50 psi flow in 100 feet of 3-inch hose, and we double the length of hose to 200 feet, the flow will also double to 100 psi. Rule 2 says that in the same size hose, friction loss varies directly as the square of the velocity of flow. If we double the speed of the flow, the friction loss is 4 times greater. And if we triple the velocity, then there is 9 times as much friction loss in the line. If we want to compare the friction loss caused by the velocity flow, we can use the following formula. Rate of increase equals velocity divided by velocity square, where v equals new velocity flow and small v equals old velocity flow. So the formula will look like this. The rate of increase equals v, big V, divided by little v square. So 200 divided by 120 equals 1.66 repeating. So now we've got to square that. So 1.66 repeating times itself equals 2.77 or 2.78, maybe even 2.79, depending exactly where you round out on the 1.66 repeating. So again, the formula is new velocity divided by old velocity square. Rule 3 states that for the same flow, friction loss varies inversely as the fifth power of the diameter of the hose. Rule 3 is by far the most important rule in the fire service. This rule is the basis for the development of friction loss coefficients. Rule 3 states that for the same flow, friction loss varies inversely as the fifth power of the diameter of the hose. There are 2 points in this rule. Point 1, friction loss varies inversely, and 2, to the fifth power. The formula for Rule 3 looks like this. Increase equals larger diameter divided by smaller diameter. So if the flow remains the same, how much greater is the friction loss in 2.5-inch hoses than in 3.5-inch hoses? And your answer would be 5.38 times as much friction loss. Rule 4 states that for a given velocity of flow, the friction loss is independent of the pressure. In general, the amount of friction loss in a given size of a hose depends upon the amount of water flowing in the hose and the speed at which it moves through the line. The pressure within the hose has no bearing on the friction loss. Although the controversy over friction loss formula may not have entirely disappeared, 2 of the most respected organizations, ISTA and NFPA, recommend the use of the same formula and friction loss coefficients for solving friction loss problems. The object of a friction loss formula is to determine the amount of loss due to friction in a certain size hose flowing at a given amount of gallons per minute. The formula is friction loss equals coefficient times the quantity in hundreds of gallons, and L equals length of hose line in hundreds. When we talk of putting the length and the quantity in hundreds, we mean this. If we are flowing 300 gallons per minute, it will be put in the formula as 3, because essentially you're doing 300 divided by 100. If we are flowing 250 gallons, we put in the equation as 2.5. And if the length of hose were 750 feet, it would be 7.5. Essentially, we're just moving the decimal place over 2 times because you're dividing both things by 100. Coefficients for a single hose can be found in table 6.1 of the text. The smaller the coefficient, the larger the line. These coefficients will be used when figuring the friction loss in hose layouts throughout the rest of the text. To determine the equivalent length of a longer line in which the same amount of water is flowing as in a smaller line, equivalent length formula is this: coefficient 1 divided by coefficient 2, the larger line, times L, which is the length of the smaller line. So, here's our problem. Water is flowing through a single 100-foot length of 1.5-inch hose at 200 gallons per minute. It is desired to replace this line and have the same amount of water flow in a 2.5-inch line while maintaining the same friction loss. How long does the 2.5-inch line have to be? So again, getting our coefficients from the chart. We have coefficient of line 1, 24, and the coefficient of line 2, the larger line, as 2. Our length of hose is 100 feet. So 100 divided by 100 will give us 1. So now we take 24 divided by 2 times 1 equals 12. Now remember that the solution is in hundreds, so 1,200 feet of 2.5-inch line will give us the same friction loss as 100 feet of 1.5-inch line. Essentially, you're replacing the 2 decimal points that we used initially to make the numbers more manageable to figure out. So that's how you get 1,200. Using the formula, examples of several pumping situations that might be encountered on the fire ground follow. There is a large amount of repetition, but repetition is the key to success. Practice, practice, practice. First question. 350 feet of 1.5-inch line with a fog nozzle flowing 95 gallons per minute. What is the friction loss in the hose only? So our coefficient is going to be 24, and we got that from our chart. We know we're flowing 95 gallons per minute, and again we're going to divide that by 100, so that makes it 0.95. And the same goes for the feet of hose, which again we're going to move that over 2 decimal points just because we're dividing it by 100, and that gives us 3.5. So now we go ahead and multiply our exponent, 0.95 times 0.95, and that'll give you a 0.90. Then we're going to multiply that by 3.5, and then we're going to multiply that by our coefficient of 24, and that gives us an answer of 75.81 pounds per square inch. So our friction loss in this problem here is going to be 75.81, or just go ahead and round it up to 76 psi. So here's our next question. You have 350 feet of a 2.5-inch line with a 1.25-inch tip, and again that's flowing 325 gallons per minute, or you can do 29.7 times the diameter squared times square root of nozzle pressure. You get that answer, and it's still going to come out to be 325 gallons per minute. So what is the friction loss in the hose? Again, our friction loss formula is our coefficient, and getting our coefficient off of that chart is 2. Then we take our Q, which is our gallons per minute, again divided by 100, so that gives us 3.25 square, and then we multiply that times the hose. So again, 3.25 times 3.25, and then times that by 2, and then times that by 3.5, gives you 73.94 pounds per square inch, or basically a friction loss of 74 psi. So let's look at this problem again in a slightly different manner. Engine 3 has laid 400 feet of 2.5 inch line, and then they reduce it to a single 1.75 inch line with an 1.5 inch coupling that is 200 feet long. The line is equipped with a 175 gallon per minute constant flow nozzle. So what is the friction loss in this layout? And what we're going to have to do is figure out the friction loss for each section and ultimately add them together. So it's going to look something like this. The total friction loss will be the friction loss in the 2.5 inch line, again, plus the friction loss in the 1.75 inch line. So, looking at our single reduced attack line here, a 2.5 inch friction loss, again, is the coefficient times the GPM divided by 100 square times the length of hose. Our coefficient for a 2.5 off our chart is 2. Our gallons per minute is going to be 1.75, again square, and our length of hose is going to be 4, because that is, again, 400 feet divided by 100 is 4. So our friction loss for the 2.5 line is only 24.5 psi. Now we look at the friction loss for our second smaller line. Our coefficient, again, off our chart is 15. Our Q is going to be the same because we're still flowing the same amount of water. So again, that's 1.75, because that's 175 gallons divided by 100, of course, square. And then our length of hose in this section is also going to be 2. We multiply it all out together, and you get 94.94 psi. We add both of those together to get our total friction loss. So in order to get the desired gallons per minute out of both lines, we need to flow a minimum pressure from the pump of 119.44 psi. So now let's look at multiple lines of the same size, same length, and same flow. If there are multiple lines that are identical, you only need to figure the friction loss for one of those lines. Do not add the friction loss in those lines together. So 2 lines are laid off a pumper. Each of them is a single 2.5 inch line, 350 feet in length, and equipped with a nozzle through which water is flowing at 265 gallons per minute. Our question: what is the friction loss for this layout? Remember, if the lines are identical, only figure the friction loss for one of those lines. So the problem is going to look something like this. What is our friction loss? So our friction loss is going to be the coefficient, again, the gallons per minute divided by 100 square times the length of hose, which is also divided by 100. So 2 times 2.65 square times 3.5 will give us a friction loss of 49.16 psi. With this type of problem, it is necessary to determine the required friction loss of the lines having the most flow. The other line or lines have to be feathered, or basically partially closed, to the correct pressure. Because remember, your fire truck will only pump the pressure, the output, at the highest pressure. So then you're going to have to close your valves a little bit on your additional lines so they also have their correct pressure and you're not over pressurizing them. So, engine 5 is pumping to 2 450-foot lengths of 2-inch hose. One of the lines is equipped with a 175 gallon per minute constant flow nozzle. The other, however, is equipped with a 200 gallon per minute constant flow nozzle. So what is the friction loss for this setup? And now, since we're flowing different GPMs, we'll have to figure out the friction loss for each. So let's go ahead and look here. We got 175 gallons per minute. The friction loss equals 8, our coefficient, times 1.75, again, our gallons per minute divided by 100 square, times our length of hose, of course, again, divided by 100, which is 4.5, equals 110.25 psi. We look at our other line, which is 200 gallons per minute. It's also going to have a coefficient of 8. However, our variables change a little bit because our gallons per minute are now going to be 2 square, and our length of hose, again, is 4.5 divided by 100. Now that friction loss is going to be 144 psi. After you add the nozzle pressure, you will pump the higher pressure of the two, and again, back down the other one to the appropriate psi. So the problem is going to look something like this. So now let's look at multiple lines being the same size in different lengths, but the same flow. With this type of problem, it is necessary to solve for the friction loss of, again, the longest line. The outlet to the other line or lines on the pumper has to, again, be feathered down to the correct pressure. So here's our question. We have two 1 3/4 lines equipped with an 1.5 coupling that have been taken off a pumper. Both are equipped with a 175 gallon per minute constant flow nozzle. One of the lines is 150 feet in length and the other is 250 feet in length. What is the friction loss for each layout? So this is what our problem is going to look like. So now all we got to do is plug in our numbers again. So our friction loss is our coefficient off the chart, which is 15.5. Again, we take our gallons per minute divided by 100 and square it, which is 1.75 times 1.75. Then multiply that by our length of hose divided by 100, which is 2.5. You figure all that out, and your answer is going to be a friction loss of 118.67 psi for our first line. Our second line, again, is very similar. Same coefficient, same gallons per minute. Our only difference is our length of hose. Plug everything in, multiply it out, and our answer is going to be 71.2 psi. So again, after adding the nozzle pressure, and we'll go into that later on what the nozzle pressures are for various things, you would set the pump pressure to the highest setting and then feather back the lower one so both lines get the correct pressure. So now let's look at multiple lines with different sizes, the same length, and the same flow. When two lines are of different size but the same length and width, the same amount of water flowing, the friction loss is that the largest line is the smallest. The outlet to the other line or lines on the pumper has to be feathered to the correct pressure. So engine 3 is pumping to two lines. Both the lines are 300 feet in length, and in both lines the water is flowing at 125 gallons per minute. One of the lines is 1.5 inches in size, and the other is 1 3/4 inches in size. Both are equipped with an 1.5 inch coupling. What is the friction loss for this layout? So our flowing rate is going to look something like this. So again, our friction loss is the coefficient times GPMs divided by 100 square times length of hose divided by 100. Getting our coefficient from our chart, our friction loss for the 1.5 inch line, again, is 24. Our gallons per minute is going to be 1.25, and our length of hose is going to be 3. Multiply it all out, and your friction loss for that line is 112.5 psi. Looking at the 1 3/4 line, our coefficient, since it is smaller, is going to be larger. It's going to be a larger line, so it's a smaller coefficient, is 15.5. Our gallons per minute is going to be 1.25 square, and our length of hose is also going to be 3. So your friction loss, after we multiply everything out for that line, is going to be 72.66 psi. So again, set the pump to the line with the highest pressure and feather the other one back to the correct pressure. So, 2 lines now with different sizes and different lengths and different flows. With this type of problem, it is generally necessary to determine the friction loss for each line and then use the one with the largest friction loss to determine the required pump discharge pressure. Then, correspondingly, gate the other lines had to be feathered back to the correct pressure. So let's look at our first problem. You have one line that is flowing 250 gallons per minute out of 150 feet of 2-inch line. You have a second line that's flowing 200 gallons per minute out of 100 feet of 1.5-inch line. What is our friction loss? So looking at our first line, we have a 2-inch hose. Our coefficient is going to be 8. Our GPMs are 2.5. Our length of hose is going to be 1.5. So our coefficient, again, is 8. Our GPM is 2.5 square. And our length of hose is going to be 1.5. Multiply it all out, and you get 75 psi. Going to our second line, our friction loss is going to be our coefficient, which is 24. Our GPMs are now going to be 2, so 2 times 2 is 4, and then our length of hose is only 100, so we divide that by 100, and that gives us 1. You multiply everything out, and our answer is 96 psi. Okay, so now let's look at it for 3 lines. You have one line flowing 195 gallons out of 150 feet of 2-inch. You have another line flowing 265 gallons out of 300 feet of 2.5-inch. And our last line is flowing 210 gallons out of 450 feet of 2.5-inch lines. So now we're looking at multiple lines with different sizes, different lengths, and different flows. With this type of configuration, you're going to have to pump to the line requiring the greatest amount of pressure and back the other 2 down. However, we're still going to have to figure the friction loss on each line to determine what our correct highest pressure is going to be. Wide lines of the same size and same length and same flow. In this book, wide lines are referred to as layouts where one line is divided into 2 or more lines. Because an equal split of water occurs at the Y appliance, to solve a problem, it is only necessary to determine the friction loss in one of the wide lines and add the result to the friction loss in the supply line. When you look at wide lines with the same size and different lengths and different flows, to solve this type of problem, it is necessary to determine the friction loss in each of the 2 lines and pump to the one having the most friction loss, and then again feathering or backing down with the gate device on the lines that require less amount of friction. Here's the layout to go through. What is the friction loss going to be from these wide lines? You have one flowing 275 gallons per minute through 300 feet of 2.5, and a second line flowing 210 gallons per minute through 400 feet of 2.5. So now let's look at the friction loss in 300 feet of the 2.5-inch line. So remember our coefficient times gallons per minute divided by 100 squared times the length of hose. Our coefficient for the 2.5 inch line is going to be 2. Our Q is going to be 2.75 and our L is 3. So 2.75 squared times 2 times 3 will give you 45.38 psi. Our friction loss in the 400 foot and 2.5 inch line will look like as follows. Again, our coefficient is 2. Our Q, our gallons per minute, is going to be 2.1. Again, that's square. And our length of hose is going to be 4. 400 divided by 100 is how we got that. You multiply it all out, and you get 35.28 psi for that line. And then our third line has a 3.5 inch supply line with a coefficient of 0.34. Now we're going to look at our total gallons per minute, and that's the total flowing from each line. So that's 485 gallons divided by 100, so our Q is now going to be 4.85. And then your length of hose is only going to be that of the supply line. So that's going to be 350 feet of that 3.5. Again, divide that by 100 and gives you 3.5. So 4.85 squared times 3.5 times our coefficient of 0.34 equals 27.99 psi. So the total friction loss equals the friction loss in a 3.5 inch line plus the friction loss in the 300 feet of 2.5 inch lines. We add it all up together and we get a grand total of 73.37 psi. Okay guys, I know this was a little repetitive, but we got plenty of math problems to keep working and practicing these things. If you have any questions, you can call me in the office or email me at aroberts@athenstech.edu. When you do the math problems, make sure you do them out step by step so I can look and see what you did, and if you got it wrong, I can point you in the right direction and point out where you made your mistake. Until next time, be safe and have a wonderful day.